Now that we've learned how to calculate covariance and correlation in R, let's look at how to do linear regression in R. So recall that in an earlier lecture we created a data set from SPSS and we made it a data frame in R called dataset. Let's take a look at the namespace of that data set. So if we just run that and we look at the resulting namespace, notice that we have several variables to work with in this particular data set, but the ones I'm going to focus on again are going to be education and father's education. So going back to my code, I'm basically going to run a linear regression model in which education is my dependent variable and father's education is my single independent variable. And this time I'm not going to attach the data. Rather, I'm going to indicate the data set that I'm going to be using in the code for the linear regression model estimation. And so in R, we can estimate linear regression models or linear models with the LM command. And then the model syntax just goes into the parentheses. And then any options we have, as usual, are followed by the comma. Okay, so here what we're going to do is we're going to do a linear model in which education is our dependent variable. The tilde is going to indicate that whatever's to the left of the tilde is the dependent variable. Whatever's to the right is independent variables. And the only independent variable that we're going to use is father's education. And then notice that I didn't use dataset and a $sign. Rather, what I did was I used the data option to tell R that my data are coming from the object dataset. So it just kind of reinforces the idea that in R, there's a number of ways to accomplish the same goal, but in different ways. And so I'm going to run this linear model, and I'm actually going to save the results in an object called model1, which is just equal to that output. So let's run that. And then if we wanted to look at the model output, we can run the summary command on the model1 object. So we run that. And if we go to our output window, here are our results. So here's the formula that we used. It shows us some of the values of the residuals. That is like the median residual, the minimum, the maximum, and the 25th percentile and 75th percentile. That's not so much of interest to us. What we're really interested in is these coefficient estimates. And so we can see that here is our slope effect for father's education. We can see that for every increase in father's education, we're predicting that the response education will increase by about 0.33 years of schooling. And then here's the intercept value, and that's predicted for somebody who has 0 years of father's education. They're predicted to start out with about 10 years of education. And then we can see these p-values or probability values. All of these are very small numbers. So this is actually in scientific notation. This tells us that we have a value of 2 times 10 to the negative 16th. So imagine like 0 and then a decimal point and then 15 decimal points and then a 2. That's how small this number is. So these two values are both statistically significant, right? And you can see that because there's a code here that tells you the significance level. So each of these is less than 0.0001. So these don't happen by chance alone. Okay, so now that we've kind of looked and interpreted the output, let's go back to the script file. Let's say that we actually wanted to look at the residuals. Well, we could do that by using the residual command. So this is a post-estimation command that we would run after we've created a regression model. So if we just run this residual command on the results of model 1, we can save that as an object, which I'm kind of arbitrarily here calling model1.res. And so we can run this, and basically then we can just plot it. So let's use a histogram to plot that object. And we'll give it a title, the residual plot for the education regression. And we'll just label our x-axis here as residuals. So if we run this and we zoom out, we see that R actually has created our plot. And we often assume that the residuals follow a normal distribution. And it looks like it's fairly close to that here. So I think it's a pretty good assumption that our residuals follow something like a normal distribution. Okay, the next thing I'm going to do is I'm going to show you how to make a predicted value from our equation. And this involves a little bit of a programming trick. So what we're going to do is we're going to create a new data frame. And within this data frame, we just have to identify values of variables that were involved in the original regression. That is the independent variables. And we only had one independent variable, father's education. And so we're just going to assign this some kind of a value. I'm going to arbitrarily choose 12 as a value. So basically what I'm going to do is I'm going to create a predicted value of the response education when the father's education is equal to 12 years. And I'm going to save that as a new object called new data. So if we run this, now if you were to run a more complex regression with more independent variables, you would also have to include values for them here. But for now, we're just going to look at the simple regression with only one indicator, only one independent variable. And so we only have to worry about that one variable. Okay, so now what we're going to do is we're going to use the predict command, and we're going to get an estimate of the Model 1 results using the independent variable values found in new data, in which case we've set father's education equal to 12. And then we have to tell it what kind of prediction interval that we want. And we're going to choose a prediction interval, meaning basically that we're just going to have some kind of range of values around this value that could include the true population parameter, something that we'll kind of get into in more detail later when we talk about confidence intervals. All right, so we're going to run this. And if we look at our output window, we can see that it gives us both a lower bound and an upper bound, which we can just ignore for right now. But basically, it's predicting that for somebody who's a father who has 12 years of education, the respondent is predicted to have about 14 years of education. So we've effectively filled in the value in the equation and predicted an outcome based on a given level of the independent variable. Okay, so the final thing that we're going to look at is just looking at a scatter diagram of these two variables if we superimpose the regression line on the plot. And so I'm going to create a scatter plot like I did in an earlier video. I'm basically going to plot the independent variable by the dependent variable. And this time I'm not going to use the data option just to show you how it works without that. This isn't attached, so I have to specify the data set that I'm using in both cases. And so this object is father's education within the data frame data set, education within the data frame data set. I give it a title. I'm going to call it Figure 1 Scatter Diagram of Father's Education by Response Education. I'm going to label the axes. So my independent variable, my x-axis is labeled as father's education, highest year of school completed father. My dependent variable, my y-axis is going to be labeled as highest year, I should spell that correctly, highest year of school completed by the respondent. And then we're just going to add a note at the bottom of the table with a title indicating that we have some number of cases, in this case 1,439. And on a new line, we're going to put the source, which is the GSS 2012, which should be left aligned. And then here we'll add yet another command, the AB line command. This is the thing that draws a line of some kind on your graph. And so we're going to draw the regression line whose results are found in the object model 1 that we created all the way up here. So if we run that set of code, and then we zoom in to the larger view, and just resize this a little bit, we can see that R has actually created our superimposed regression line on our scatter diagram. So we saw the scatter diagram before in an earlier video. This is what the best fit line looks like. So notice that it's crossing the x-axis right around the value of 10, which is the intercept, and that our slope is telling us how steeply pitched the line is. And as we suspected, it's a line that sort of has a moderate fit to the data, and it looks like it's a positive relationship. So as father's education increased, so does the respondent's education. And then if we wanted to, we can kind of go back to our regression results to look at the fit of the model. And so we can see that the R-square value here is 0.2126. So that indicates kind of actually like a fairly low fit. Only about 21% of the variation in education is explained by father's education. And so that's consistent with this value, indicating that we have a lot of points that really are not very close to the line, indicating not the best fit. So that means that there are probably a number of other kinds of factors that explain education other than just father's education. And so with that, that's basically how you estimate a linear regression model and predicted values and residuals in R.